Zoom is not always very kind to me. So thank you. And thanks for the kind invitation. It's an honor to be part of this speaker series. I also want to thank Brian for allowing me to present from Pullman. I know it's more fun for everyone, including me, if I could be there in person, but it's become a priority to take every opportunity I can to try to reduce my carbon footprint. And I couldn't justify traveling all the way down the coast to give a talk that I could just as easily give over Zoom, or apparently I could easily give it over Zoom. Maybe that's not the case. So thanks for letting me participate without taking a plane down to LA. And speaking of Zoom, our campus internet gets a little bit bogged down in the middle of the day. So I'm going to present with my camera off, and I'll turn it back on for the Q&A. I've learned the hard way that leaving it on significantly increases the likelihood that our overworked Wi-Fi will fail while I'm presenting. So I want to avoid any further delay. Okay, so without further ado, on to the talk for today. For the last 10 years, my overriding research interest has been trying to figure out when and where, maybe even why, high fidelity social learning, AKA what most people call cultural transmission, evolved on our lineage. And as you know, cultural transmission, the kind we engage in every day, can facilitate so-called cumulative culture. It can also support marked regional differences within a spatially structured population. Most of us simply call these things cultural differences. So some people eat with chopsticks while others eat with forks. Some people speak Mandarin, others speak French, and so on. The boundaries between these cultural differences are imperfect, of course, but the extent to which they still tend to hold in the modern world is perhaps somewhat surprising, given the large-scale movement of ideas around the globe. So this suggests to me that the varied mechanisms of cultural transmission are pretty powerful forces for defining and maintaining boundaries between groups in a spatially structured population. Okay, hopefully that slide advanced for you.
Yep.
Okay, good. So although largely a purview of population genetics, structured population models have become more prominent in cultural evolution over the last couple of decades. A structured population just refers to a population that is divided into groups. The size and number of groups, as well as the rules individuals must follow to move between them, provide the population's quote unquote structure. So group mates interact with each other more frequently and or in different ways than with members of other groups. And although an individual can be a member of just one group at any point in time, group membership can change through time as a result of migration between groups. In population genetics, structured population models often provide powerful tools for understanding how the four forces of evolution, of course, mutation, gene flow, genetic drift, and selection, shape genetic variation within and between groups. And the findings of these models have had wide-ranging implications for agricultural production and wildlife management and conservation. Now, the fact that many human interactions, including cultural transmission, are structured to a large degree by group boundaries, means that structured population models also have much to offer researchers interested in building a better understanding of how cultural evolutionary forces, that would be copying error, intergroup transmission, drift, and selection imposed by functional constraints, or perhaps by biased mechanisms of transmission, how those affect how cultural variation is partitioned within and between groups. And although they may not use the term structured population very often, archaeologists have employed the predictions of such models as expectations for their empirical work. In fact, archaeologists have a long-standing interest in delineating boundaries that mark regional cultural differences, going all the way back to the culture area approach of the early 1900s and the subsequent cultural ecological approach of Julian Stewart. And over the last 25 years or so, Paleolithic archaeologists have become more and more interested in studying boundaries between cultural groups in the past, for what seemed to me to be two largely unrelated reasons, both interesting. The first has to do with the fact that some researchers list regional cultural differentiation as a hallmark of so-called quote unquote behavioral modernity. For those interested in identifying the origins of this modern behavior, the argument goes something like this. If archaeological evidence of some distinctive regional cultures is thought to serve as evidence of behavioral modernity, then modernity is at least as old as the earliest evidence that we have of these regional differences. It's a bit circular, right? But it depends upon the first part of that being true. Second, and more recently, regional cultural differences have become important to researchers interested in trying to better assess the degree of spatial structure that marked early Homo sapiens populations in Africa. So researchers like Scary and her colleagues have looked to cultural variation within and between geographic regions as an indirect means to study structure in the biological populations that can't be observed directly because they're gone. So the assumption here is that regional cultural differentiation between assemblages of artifacts reflects past structure in those populations that ultimately are the interest of these research questions. Now, surely past hominin populations were structured. I mean, certainly they could not have been panmictic. But the question these kinds of studies raises is are the archaeological assemblages really the best window we have into that structure? And they may be the best window, but I guess we go a step further and ask whether we see an accurate picture through that window, even though it may be the best one that we have available to us. And I think my current project can contribute something to another topic, but I'll get to that in a moment because I want to try to illustrate how people have gone about trying to study and delineate these regional cultural groups. That is how they try to identify past boundaries between what they infer to be different, culture groups in quotes. So the examples that I know of are based on the simple premise that a cultural boundary ought to result in a greater degree of cultural differences between the assemblages that formed in the regions that were separated by said boundary than what we see within those regions. So if, for instance, in this little cartoon, the population-wide variation in chopstick use versus fork use was explained almost entirely by membership in these two different groups, then one would likely consider that pattern to be evidence of some boundary between them represented by this thick black line. To the contrary, if members of both of these groups use both types of utensils roughly to the same degree, then we'd probably see this as a cultural similarity, not a difference between the groups. So one probably would not infer a boundary in this scenario because there's no difference between the groups, at least with regard to this one single trait. All right, so it seems simple enough, right? Look for big differences between groups or between assemblages of artifacts, and then you've got some evidence of a boundary between the cultures. But I'm going to argue that maybe this isn't quite so easy when applied to Paleolithic assemblages. And more specifically, I'll show you some results that indicate it might be difficult to see cultural boundaries that were actually there in the past. But we're going to get to that later in the results. I also want to tell you about this other aspect that I think the results of this project can speak to. So in addition, I think these results also have something to say about my longer term research interest, which I said before was trying to figure out when and where cultural transmission evolved in our lineage. And archaeologists have become more interested in this topic as of late. Instead of simply presuming that any old stone tool must have required cultural transmission, which has been kind of the default since at least the 1950s or so, it seems some researchers are open to considering alternatives by which early stone tools might be able to persist in the absence of the kind of high fidelity social learning that we call cultural transmission and that we know of from our own societies today. In light of this possibility, the mere presence of an Oldowan chopper or an Acheulean hand axe may no longer serve as evidence of cultural transmission as it had for a Paleolithic archaeologist before. And I think the results can help us address this issue as well. Although I won't be addressing it directly. I think that this kind of the work that I'll be showing you hopefully helps move us down this road a little bit further than we've gotten so far. And the results I'll be presenting today that have to do with this topic come from a paper I'm currently working on with Jelko Rezic. Here you see him pictured. Jelko is a Paleolithic archaeologist with expertise in stone tools. And the picture here shows that he's in what looks to be a rather hostile environment for conducting research, but this is the kind of fieldwork that he does. We started this project during my sabbatical at the Department of Human Evolution at the Max Planck Institute for Evolutionary Anthropology when he was doing his postdoc. And unlike the picture on the left, the picture on the right of the Institute shows an extremely pleasant environment for doing research. And that's mainly because of the great people there, like Anna Conler and Shannon McFerrin, and many others. And of course, the beer is also very good. So a few weeks into my sabbatical, Jelko came into my little my cozy little guest office. I was kind of stuck between some bookshelves and a safe that had a bunch of fossils in it, actually. But it was a great little spot, and I was, of course, very, very happy to be back at the Institute and meeting new colleagues. And he came and he introduced himself and said he was very interested in learning more about cultural evolution, because many of his colleagues in Paleolithic archaeology were starting to infer mechanisms of cultural transmission from archaeological data. He had a recent archaeology paper with him that had sparked his interest. I hadn't seen it before, and to be honest, I don't recall what paper it was now. As I remember it, the gist of the conclusion was something like, after comparing these X assemblages, we conclude that they serve as evidence of conformist bias transmission at this time. So the authors had rather confidently inferred the presence of conformity in Paleolithic groups based on their study of the lithic assemblages from, I think it was 2 or 3 different regions. So he asked me if their conclusions seemed warranted, given the values that they had. And I gave him my most frustrating but honest answer. And that was, well, it depends. It depends on what, he replied. Well, it depends on the answers to these questions, among others, I think. This is a list of some of the questions that Jelko and I tackled over subsequent conversations about, like how do we evaluate these interpretations based on the empirical work that's done. And I'll go over these in more detail in the discussion part of the talk. I just wanted to foreshadow them a bit here because they do serve as a motivation for the model that I'll be telling you about. And I also want to preview the takeaway message of the study right now and return to it again at the end. And that is that when attempting to infer mechanisms of cultural transmission, as Jelko's colleagues were doing in that paper, or when trying to identify boundaries of past culture areas from archaeological data, I think it's crucial to be precise about the nature of the cultural traits that we have to study. These details matter when it comes to interpretation. So the answers to these questions really matter. And in my opinion, most of the studies, at least that I know of, they don't do a great job of addressing these questions before jumping right into their interpretations. And I think we can do better. And I'm going to try to convince you of that with the presentation today. So through my continued discussions with Jelko, it became clear that it would be useful to create a simple structured population model to help illustrate to others why this list of questions is important. So as I said before, this serves as a motivation for the model that I'll be presenting to you right now. Okay, so the purpose of the model is to illustrate how these 5 factors, which are taken from my previous list of questions, number 3 through 7, that's why they're 3 through 7 rather than 1 through 5, how these 5 factors influence between group and between assemblage differences in a single, selectively neutral, discrete cultural trait. And this trait can be passed via one of 4 different mechanisms of cultural transmission. So I'm going to go through the basics of the model rather quickly because I want to give you just enough that you can appreciate the results without us spending the rest of our time here on model description. But of course, I'm happy to go over the model in more detail or answer questions during the Q&A period afterwards if there's something that isn't clear here. But it's a fairly simple model, and so hopefully I can do it justice in just a few minutes here. Okay, the population is structured into 25 groups, each of which contains 25 individuals. And that gives us a constant population size of 625 individuals. This is not meant to represent any real Paleolithic hominin population. Okay, so you don't have to worry about the numbers here so much. Each individual displays a variant of a selectively neutral, discrete cultural trait. And the categorically different variants of the trait are represented by integers in the model. On the slides, I'll use color to represent those different variants as well. But in the model itself, they're just represented by different integers. And agents engage in 2 different behaviors during each time step of the simulation. They engage in cultural transmission from the experienced generation to the naive generation within each group. And then a subset of them will also have a chance to engage in intergroup transmission. The so-called naive generation replaces the experienced generation at the end of each time step, and this is what maintains our constant size population of 625 throughout each simulation run. Okay, so a bit more about these two behaviors that agents can do. Here's how cultural transmission within groups works in this model. So during the course of each time step, an experienced agent might transmit its cultural variant to at least one naive member of its group. Each cultural transmission event has some probability of being marred by a copying error, right, in which the naive individual does not adopt the teacher's variant, but rather adopts something different by mistake. And that's going to be represented, copy errors can be represented with this red X, like in the slides, the results slides that follow. So with probability 1 minus mu, the naive individual adopts the teacher's variant, as seen here, with everything going as planned, right? No problem here with this transmission. It gets the 5 just like it was supposed to from its teacher. But with probability mu, the naive individual gets a different variant due to some kind of noise in transmission, all right? And that's what's represented by this red X. But which variant does it get, right? So there's been a mistake here, but it's not going to get a 5, but what is it going to get? Well, that depends on which copy error model we use. Under the infinite variance model, each copying error results in the naive individual adopting a novel variant, right? This is an integer that has never been displayed in the population before. It's something that's completely new and has never been displayed by an agent to this point. Okay, and there are infinitely many of those. Under the finite variance model, each copy error results in a naive individual adopting one of the other possible variants, whereby the number of other possible variants is capped, right? So there's some kind of ceiling value on the maximum number of variants. You might think of this as the number of ways there are to skin a cat, so to speak. So I'll use the cat icon to represent this maximum number of variants under the finite variance copy error model. So if the ceiling is 10 possible variants, then that means that the naive individual will adopt one of the other 9 variants with equal probability, right? So it won't get a 5, but it will get one of the other possible variants. And which one it gets, there's an equal probability that any of them could be chosen. So note that while variants can be rediscovered, so to speak, through copying error in the case of the finite variance model, that is not possible with the infinite variance model. So in the infinite variance model, once a variant has disappeared from the population through drift, then it cannot reappear. But they can reappear through copying error in the case of the finite variance model. I also model 4 different mechanisms of cultural transmission within groups. These are color-coded, and those colors will match their box plots in the figures, or in the results figures that I'll show later. So with unbiased transmission, ego learns from a randomly chosen experienced member of its group with replacement. Under vertical transmission, in red, ego learns from its asexual parent. So in this case, every experienced agent teaches one naive individual. This means that there is no drift with vertical transmission. Under conformist transmission, in green, ego adopts the modal variant of its group. Right? So that which is displayed most frequently in the group. And under prestige bias transmission in yellow, ego learns from the most prestigious member of its group. And the prestigious one is chosen randomly at the start of each time step. So unlike with unbiased transmission, every naive individual in the group will learn from the same prestigious individual, even though that prestigious individual is chosen randomly at the start of each time step. All right, so those are the 4 transmission mechanisms that I will be investigating here as well. Okay, the other behavior is intergroup transmission, which you might also think of as migration, right? Because there's no copy error involved here. I wanted to keep copy error just to the within group, from experience to generation to naive generation. And I wanted to just have intergroup transmission independent of copying error. That's really the only reason why I programmed it this way. So I've operationalized this as something more akin to migration, but really it's just eliminating that additional source of copying error. So each time step, a small fraction of the population's experienced individuals, and I use 3 different values here, either 0, where there's no intergroup transmission, 6 out of the 625, which is roughly 1%, or 30 individuals, which is roughly 5%. they will swap integers with members of different groups. This occurs before cultural transmission from the experience to naive generation within each group. And I will represent this intergroup transmission with this little suitcase icon in the results figures to come. So to illustrate how this works, suppose this guy here is one of the randomly chosen agents for intergroup cultural transmission. So first, one of the other 24 groups is chosen at random to find his partner. Then an experienced member of that group is chosen at random, and they swap cultural variants. You can also think of it as I said, migration, where they swap places, if you like, because there's no copy error here in this case. So an intergroup transmission rate of 0 represents strict boundaries between groups, right? In that case, people and variants do not pass between groups when we've got that set to 0. So far, this structured population model would look pretty familiar to a population geneticist. But we have to keep in mind that archaeologists work with a very different kind of data set. Archaeologists work with assemblages of cultural material, not populations of toolmakers and users. And this is an important distinction. Assemblages, unlike populations, can become time averaged as they accumulate artifacts that are deposited by different populations through time. So you'll recall one of my questions from before was about time averaging. How might time averaging affect one's ability to accurately recognize mechanisms of cultural transmission or to identify boundaries between past culture areas? And to study that, I allow for each experienced individual to deposit its cultural variant, just its integer, in the archaeological assemblage of its group. Artifact deposition occurs with probability 0.01 per agent per time step. So the resulting assemblage represents a random 1% sample of the cultural variants displayed throughout the entire simulation run. Or I should say over the last 10,000 ticks of the simulation run, which just corresponds with the dynamic equilibrium condition of the model with respect to the cultural variant richness. So this cartoon population would leave behind some artifacts, right, represented as integers in the simulated archaeological record. The next generation would deposit some of its artifacts as well, right, a 1% sample, and so on. So you see that material accumulates in each of these cells through time. So each cell or region, if you will, serves as a container for its own archaeological assemblage. The resulting assemblages can then be compared to each other in the same way that archaeologists compare assemblages that accumulate in different regions of Africa, the Levant, or Europe. So to assess the effect of increased time averaging, I studied assemblages that formed over 1,000 time steps and then 10,000 time steps. And I can compare those assemblage results to data collected from the population at time step 20,000, the last time step of the simulation. All right, so I can look at not only the effect of time averaging, but I can compare the assemblage results back to what a population geneticist would be interested in, which is the population at a particular time period or a particular time step. Okay, a bit about initialization and data collection, and then we'll be ready to look at the results. So at initialization, all agents are randomly assigned one of the possible finite variants. So in this case, you see there on the lower left that the max was capped at 10. So this means we start with relatively low between group differentiation and relatively high within group diversity. This is what we do for the finite variance case. In the case of the infinite variance model of copy error, which is not pictured here, but I will show you some results under those conditions. Every agent gets its own unique variant at the start. So this results in very high within and high between group variation at the start of the simulation. Okay, so regardless of those starting conditions, I let each simulation run for a 10,000 time step burn-in period. And this gets us to the equilibrium condition in the population. And here I'm looking at equilibrium invariant richness, right? So where richness, if we're starting out at a high value, where it decreases but then plateaus, or if we were to start from a homogeneous starting condition, which we're not in these cases, but then it would be where variant richness increases and then flattens out. And under all of these conditions, within, it's usually before 10,000 time steps, but at that point, we've reached that plateau. At that point, then I allow the experienced agents to start dropping their artifacts with probability 0.01 per agent per time step. So I'm only collecting the assemblage data after this equilibrium point has been reached. Then assemblages form over the next 10,000 time steps. I collect data at the very end, so at time step 20,000, right before the simulation ends. And first I get a snapshot of the population. Okay, so this one has an assemblage duration of 1, which is just referring to the population and not to the artifacts that have accumulated over time. Then I harvest assemblages that accumulated over the last 1,000 time steps. So from 19,001 to 20,000. And finally, I collect the assemblages that formed over the last 10,000 time steps. So from tick 10,001 to 20,000. So these are the most heavily time averaged assemblages. Okay, as for data collection, although I calculated a few different metrics from the assemblages, the one that's most important to us today, given our focus on boundaries and our focus on trying to infer mechanisms of cultural transmission, is a measure of cultural differentiation among assemblages. This is what the archaeologists, this is kind of where the archaeologists tend to go, although they don't necessarily use this particular measure. And I can also calculate this among groups in the population level data. So it's not just applied to assemblages, but also I can apply it to groups. So I use a fairly common measure called mean pairwise difference to quantify the extent to which assemblages differ in the relative frequencies of the cultural variance. So for the purpose of a very quick illustration, consider 5 assemblages that contain just 10 artifacts each. Of course, my assemblages from the simulation contain far more, but this is just to illustrate how this measure works. And in this case, each artifact can display one of 5 possible cultural variants. I've represented them here with different colors, but in the model, they would be represented with different integers. So perhaps these are 5 different ways to make some kind of stone tool. These might be considered 5 different technologies for making what to you and I might look like a similar implement in the end, but there would be different ways to get there. This extreme case, in which the artifacts in each assemblage display a different variant from the other assemblages, results in the highest possible mean difference value of 1. Okay, so you see here that you make a pairwise comparisons between each of these 5 assemblages, and the sum of those gives you the mean pairwise difference for each. And then to get the mean difference, right, so the difference overall, you just take the average of those mean pairwise difference values. So you would sum them, you get 5, you divide by 5 because we have 5 assemblages, and that gives you the highest possible value of 1. And you can see why, right? Because each of those assemblages has 100% of a different variant of this trait. Here's a less contrived case in which every assemblage displays many of the possible variants, but at different relative frequencies. So this results in a lower mean difference value. In this case, it's 0.5. And that's because the assemblages are more similar to each other in their cultural variants than we saw in the previous example. Mean difference would be 0 when all assemblages display exactly the same mix of variants. Their relative frequencies would all be equal in that case. So this mean difference value ranges from 0 to 1, from no difference between assemblages to maximum difference between assemblages. And the difference we're interested in here is the relative frequencies of these different cultural variants at this one single selectively neutral discrete trait. Now, in addition to studying group differences, cultural evolutionists have also been interested in cultural turnover rates. So given this interest, I thought maybe it would be prudent to also collect data on cultural turnover within the groups in my structured population model. This wasn't my initial focus, but I collected these data, and I thought maybe some of you would be interested to see how this plays out. So I'll show these results as well. Now, my turnover events are defined a bit differently than they are in these papers. So in my case, a turnover event is defined as any case in which the modal cultural variant in the group at time t+1 is different from the modal variant of that group at time t. So you see that illustrated here in this cartoon with colors. The modal variant goes from the red one to the black one. So I would count that as one of these turnover events within this group. And here I should note that Paleolithic archaeologists can't really study turnover events within a time averaged assemblage because by definition, time averaging obliterates this temporal signal of change through time. But in the simulation, I do have access to these data. So starting after that 10,000 ticks burn-in period, I start collecting data on these cultural turnovers in each group. And I do that for the remaining 10,000 time steps. So at the end of the run, then I can calculate the mean number of turnovers per group over that 10,000 time step period. And that's what I'll be showing you in the results figures. Okay, now that's quite a bit to remember about the model, even though it's fairly simple. There are quite a few details there. And I don't want you to lose sight of the purpose of the model, okay? Remember that the question I'm setting out to address is this one. How does copying error, intergroup transmission, and time averaging affect the degree to which regional assemblages differ at a single selectively neutral discrete trait passed via one of 4 different mechanisms of cultural transmission? Or in pictures, I might represent it this way. How does all this stuff on the left, those things that I've introduced you to now through the model description, how does all of that stuff affect the mean difference among regional assemblages? And also, I'll also show you that turnover rate data as well, the turnover rates within groups. If there's no effect, then we don't have to worry about all those pesky questions I listed near the start of the talk. If there is an effect, then perhaps that might convince some to pay more attention to some of those questions. Okay, so let's have a look at some of these results. All right, I'll start with results from conditions that I think are more closely related to the PopGen models of structured populations. Not because I think they're particularly applicable to archaeological data, but because I think these are the expectations that archaeologists most routinely draw from, and that may be unfortunate. And the reason why I say these particular conditions are closer to the PopGen models is because here we're looking at the infinite variance model of copy error, which you see indicated there in the upper left of the slide. Remember, under this model of copy error, we assume that each and every mistake introduces a novel variant of the cultural trait. Now, clearly, this is unlikely to be true of any discrete attribute of a stone tool, for example, right? There aren't infinitely many ways that you could make a mistake. But we're going to go with this for now, right? And then I will show you the results then from the finite variance model, which I think is more applicable to the archaeological case. Note that each box plot represents data collected from 30 unique simulations, and that these box plots are color-coded by cultural transmission type, right? So blue is unbiased, red is vertical, green is conformist, and yellow is prestige biased. And I defined those a few slides before. And here in this panel here, we're looking at the effect of time averaging on mean difference for each of the 4 mechanisms of cultural transmission. The copy error rate and the intergroup transmission or migration rate, if you will, are both set to their medium values. So I chose low, medium, and high values, arbitrarily for these experimental parameters. These values aren't meant to correspond to any, thing I think about reality for the Paleolithic. I just chose these to vary them and to look at the sensitivity and the effects under different copy error values and intergroup transmission values. Here we're holding them constant though for this one panel. As we move from left to right on this panel though, so along the x-axis, notice that we are increasing time averaging. So the far left side of the panel is the population at time step 20,000, so there's no time averaging at all. Then the middle set of box plots comes from assemblages that accumulated over 1,000 time steps, right? From 19,001 to 20,000. And the right set comes from assemblages that accumulated over the last 10,000 time steps. So you see the little time averaging icon getting bigger from left to right. That is illustrating that we have greater time averaging to the right. So under these conditions, you see that time averaging affects mean difference for 3 of the 4 transmission mechanisms. Mean difference is unaffected by time averaging under conformist transmission. Under these conditions, conformist transmission results in extremely high between group differences that persist for the entire period of 10,000 ticks, and thus they also appear in the time averaged assemblages. So in this case, when we have conformist transmission, each group kind of locks in a different variant, and then it can never be replaced. A brief sidebar here, though, the very high mean difference observed under conformist transmission is due in part to how the simulations are initialized. So if we start all agents with the same variant rather than with a unique variant, which is what we're doing with the infinite variance condition here, then conformist transmission yields extremely low mean difference values, right, close to 0, even under the infinite variance model of copy error. Note that the other 3 transmission mechanisms yield the same values under this homogeneous starting condition. So in this case, the conformist transmission results are sensitive to that starting condition. And that's worth making clear here. I'm still going to stick with the heterogeneous starting condition for most of these results, but this is something that I will be addressing in more detail in the paper, so that it's clear that with this one case, the starting condition really matters. But for the other 3 transmission mechanisms, time averaging has a negative effect on mean difference. That is, time averaging makes the regional assemblages appear more similar to each other than the groups would have been at any point during the simulation. It's also worth noting that the unbiased transmission results in blue and prestige biased transmission results in yellow yield similar values to each other while controlling for time averaging. So in these cases of overlap, it would be impossible to discern among these 2 transmission mechanisms given just a mean difference value. So this is already quite interesting and maybe a bit concerning for inference. But what about how the effect of time averaging is modulated by copying error probability and by intergroup transmission? Remember, those were questions that I wanted to address and to hopefully illustrate the effects with this model. Both of those are held constant at their medium value in this panel, right? Because we're not varying those things, we're just varying assemblage duration. But of course, we can look into that, and I did with my experimental design. So here I've kept the middle panel from before. You've already seen that one. But I added panels to the left and the right to illustrate how copy error probability modulates the effect of time averaging on mean difference. Okay, so we're going from no copy error on the left to higher copy error on the right. Mean difference is not affected by time averaging under conformist bias transmission, under any of these conditions. And that is because all of the new variants introduced are effectively ignored so long as they don't change the modal variant in the group. The left panel shows that when there is at least some intergroup transmission, but no copying error, time averaging has no effect on mean difference under unbiased and prestige biased cultural transmission. And this is because the combination of drift within groups and migration between them renders all groups the same at equilibrium. So, all agents at time step 10,000 display the same cultural variant. And because there's no copying error to introduce new variants, they will keep that through the rest of the time. The center and right panels show that under these conditions, increasing copy error probability attenuates the effect of time averaging on 3 of the 4 mechanisms of cultural transmission. The right panel also shows that when mistakes are fairly frequent and when each copy error yields a completely new and novel variant, then all 4 transmission mechanisms are associated with very high mean difference values. And again, that's with this starting condition in which every agent starts with a unique variant. If we started with a homogeneous case, then the conformist transmission would be low rather than high. So, does this mean that a mean difference value of 0.9 always indicates conformist bias transmission within groups, and or does it always serve as evidence for impermeable boundaries between different cultures? No, not necessarily. It depends on other factors, because this shows that there are multiple ways to arrive at relatively high mean difference values, which is what you see there in the right panel. Again, given the conditions of these simulation runs. And now we can hold copy error probability constant at its median value, 0.001, to investigate how intergroup transmission rate modulates the effect of time averaging on mean difference. Again, starting with the left panel, where there is no transmission between groups, time averaging has no effect on mean difference for any of the 4 cultural transmission mechanisms investigated here. So under these conditions, mean difference provides no leverage to discern among the 4 different kinds of transmission. However, these very high mean difference values are indicative of the presence of strict boundaries between groups. Then from the center and right panels, we learned that increasing intergroup transmission amplifies the negative effect of time averaging on mean difference for 3 of the 4 transmission mechanisms. As for the 4th, mean difference is not affected by time averaging under conformist transmission. And this, again, is because all the new variants introduced to a group, either through copying error or intergroup transmission, are effectively ignored so long as they don't change the modal variant in the group, which is what the naive individuals would learn. Okay, now let's move on to results from conditions that I think are closer to the archaeological application. And I say closer here because now we're using the finite variance model of copy error, by which we assume there are only, in this case, 5 different variants of the cultural trait, and that each copy error results in one of the other 4 being chosen. Okay, so under these conditions, there are only 5 ways to skin the cat, so to speak. Again, the copy error rate and the intergroup transmission rate are both set to their median values for this panel. And as before, as we move from left to right on this panel along the x-axis, we are increasing time averaging, right? And again, we're still looking at the mean difference value here. So under these conditions, time averaging affects mean difference for 3 of the 4. As before, conformist transmission is unaffected by time averaging. However, here again, for the case of conformist transmission, the mean difference values are sensitive to the starting condition of the simulation, right? So you see here that if we were to start every agent with the same variant, rather than one of the 5 possible variants, conformist transmission would be associated with the lowest possible mean difference values, right? In this case, the same variant gets locked in all of the groups, so there's no difference between them because they all start out with the same variant. However, you can see that the other 3 transmission mechanisms are not as sensitive to this starting condition as conformist transmission is.
Luke. Maybe we have exceeded the transmission bandwidth of Washington State's cultural technology. I don't have his notes, but I assume he's anticipating to continue on here. I'm going to pause it. Oh, okay. He'll probably join in a second. Oh, there he is. Hey, Luke, are you joining us? There you are.
I'm back. I'm sorry. As I feared, I got kicked off of my system here.
Yeah, you warned us. We're ready for it.
I know. Sorry about that. Okay, let's see. Do you see this again now, the slides, or no?
Not yet. No.
Okay. And let me
see if I've got to make you co-host once again.
I see it here. Let me try.
Yep, that's the regular view. If you hit slideshow and then do the switcheroo on the displays, that might work. Perfect.
Good again?
Yep.
Okay. Sorry. Hopefully that won't happen again. Okay.
You were telling us how starting conditions matter.
Oh yes, for conformist. Okay. Now again, we see that unbiased and prestige biased transmission yield similar mean difference values when we control for time averaging. And also note that in this case, vertical transmission yields similar values to more time averaged assemblages that formed under unbiased and prestige biased transmission as well. So as a result, there are multiple ways to arrive at a mean difference value of, say, something like 0.13, right? If you didn't have a prior information about the time averaging of the assemblages or of the type of cultural transmission mechanism, it would be difficult to recover either of those from this just given a value of 0.13. So this is an example of equifinality in action. So here I've kept that middle panel from before, but I want to investigate the effect of copy error probability and how it modulates the effect of time averaging on mean difference under the finite variance model of copy error. Okay, so as before, time averaging does not affect mean difference under conformance bias transmission. That's the same in all three panels. The left panel shows that when there is some intergroup transmission, but no copying error, time averaging has no effect on mean difference under unbiased or prestige bias transmission. And again, this is because the combination of drift within groups and intergroup transmission between them renders all groups the same at equilibrium. All agents show the same cultural variant by time step 10,000. The left panel also shows that time averaging has a negative effect on mean difference in the case of vertical transmission, even in the absence of copying error. Remember, there is no drift under vertical transmission, so that's why it's different from the blue and the yellow data points. The center and right panels show that, if anything, time averaging has an even greater negative effect on mean difference when copy error rate is higher, at least for the unbiased and prestige biased mechanisms of cultural transmission. So these results illustrate to me how the combined effects of copy error and time averaging vary quite a bit by transmission mechanism, which on the one hand is interesting and probably good to know. On the other hand, it may make our ability to recover these different transmission types from the archaeological record more difficult. And here we're looking at the effect of intergroup transmission rate while holding copy error constant at its medium value. The left panel represents a condition in which there are strict boundaries between groups. So there's no movement between groups when that's set to 0 individuals moving between them. And note that even when there's some time averaging, so at assemblage duration 1000, unbiased and prestige biased transmission both result in pretty high mean difference values. Values that are comparable to what observes under conformance bias transmission, at least under these starting conditions. And this marks a case where high mean difference does not necessarily mean conformist transmission within groups. And sticking with the left panel, note also that vertical transmission yields relatively low mean difference values, despite the fact that there was no contact or migration between groups under these conditions. In other words, the strict boundaries between groups are not as apparent in the assemblages that formed under vertical transmission as they are in those that formed under the other three. Along similar lines, in the presence of some copy error, time averaging eventually reduces the mean difference values for unbiased and prestige biased transmission, as you see there for the assemblage duration of 10,000. They effectively erase much of the evidence that there were in fact strict boundaries among the groups that dropped those artifacts through time. The other two panels show more or less the same negative effects of time averaging on mean difference for 3 of the 4 mechanisms of cultural transmission. So there's nothing much new to report from those panels in this case. Now here we can investigate the effect of increasing the maximum number of cultural variants from 5 to 10, right? I've kept it at 5 for the last few slides. You might be interested in what happens when that gets increased. So even though this isn't much of an increase in absolute terms, you can see in the right panel that even this increase from 5 to 10 tends to yield higher mean difference values for all 4 of those transmission mechanisms. Remember, it's only the maximum possible number of variants per trait that varies between these panels. Everything else is the same. So the fact that the expected values, if you will, of mean difference vary with the maximum number of variants that can be actually for a trait is one of the reasons why it's important to be precise about how many different variants of a trait there could be when you are formulating your expected values for a mean difference that then you can compare to what you actually observe empirically. Okay, so far we've been looking at results of pure transmission mechanisms. That is to say, all transmission events from the experienced to naive individuals are of the same kind, either unbiased, vertical, conformist, or prestige biased. And these are depicted in that left panel, and they're depicted with different colors. But if we relax that assumption to allow each of the transmission mechanisms to occur with equal probability during a simulation run, what do we see then? What do we see under this kind of mixed transmission condition? Well, the panel on the right presents the mean difference values for this mixed case, whereby each of the 4 transmission mechanisms occurs approximately a quarter of the time within each simulation run. So again, here, even with this mixed condition, we see the time averaging has a negative effect on mean difference, such that the heavily time averaged assemblages tend to look more similar than the groups that drop the artifacts. And although the mean difference values of the mixed condition don't overlap perfectly with any of the individual mechanisms on the left, it looks like the values are most similar to prestige bias transmission. They look least like the values associated with vertical or conformist, even though both of these occur just as frequently as prestige biased and unbiased transmission. They all occur with equal probability. So if you were interested in what it looks like if it's a little bit more complicated, here you see the mixed transmission condition results. Okay, and I told you I'd give you a look at the cultural turnover results as well. So let's shift gears now and have a quick look at those. I'm only going to show you these for the finite variance copy error model case, just to cut down on time a little bit here. So the mean number of turnovers per group gives us a sense of how frequently there was a change in the modal variant within each group over the course of the 10,000 time steps at equilibrium. And remember, although archaeologists might be interested in these turnover rates of cultural variance, this is something they simply can't recover from time averaged assemblages. I collected these data for each group during the last 10,000 ticks of each run, right? So, of course, unlike archaeologists, I have full access to all the data during these simulations. And essentially, I was doing ethnography during each run rather than doing archaeology after each run. Also note that this graph looks a little bit different than the previous ones that we've been looking at. Here, the x-axis represents variant ceiling rather than assemblage duration, because I'm not getting this from the assemblages, right? I'm getting this in real time as I'm observing what's going on in each of these groups. So you'll be able to look at the effect here of variant ceiling on mean turnovers per each of the 4 transmission mechanisms. And this panel provides the turnover results for the medium values, again, of copy error probability and intergroup transmission. You see those details again up in the upper left of the slide. So the highest turnover rates are observed under unbiased transmission, the blue one there, then vertical, then prestige biased. And there were very, very few turnovers under conformist transmission. And this is true regardless of whether the simulation is initialized with every agent displaying the same variant or every agent displaying one of the possible finite variants, either 5 or 10 in this case. All right, so in this case, conformist by the mean number of turnovers per group under the conformist bias transmission condition is not sensitive to the starting condition in the same way that the mean difference was sensitive under conformist transmission. So let's look at the effect of copy error probability on the effect of, in this case, variant ceiling, or the max number of different variants per trait. The middle panel is the same one from the previous slide, but the panels on the left and the right are new. First, note that copy error rate and variant ceiling do not affect mean number of turnovers. Under conformist transmission, it is essentially 0 in all cases. The left panel shows that when there is some intergroup transmission but no copying error, variant ceiling has no effect on mean turnover under unbiased, prestige biased, or conformist transmission. Those are all very low. But it also shows that in the case of vertical transmission, intergroup transmission alone can cause turnover within groups, even in the absence of copying error. Now, of course, this would also be a different story if we had initialized the population with the same variant instead of all the possible variants, right? If they all started with the same variant, then vertical transmission would not be showing a higher value there of the number of turnovers. It would be 0 across the board. So this result for vertical transmission is sensitive to that particular starting condition of the model. The center and right panels show that mean number of turnovers increases as the probability of copying error increases for 3 of the 4 transmission mechanisms. And this is what one would expect, at least for those 3. Under unbiased transmission in blue, and to a lesser extent, under prestige bias transmission in yellow, the mean number of turnovers is greater when the variant ceiling is higher. However, under vertical transmission, the red one, The mean number of turnovers is slightly higher when the variance ceiling is lower, interestingly enough. Overall, increasing copying error has the greatest effect on mean number of turnovers per group under unbiased transmission, the blue one, then vertical, then prestige biased transmission, and increasing copying error has no effect under conformist transmission. Here we're looking at the effect of intergroup transmission rate and how that modulates the effect of variance ceiling on the turnover data. So the left panel here represents a condition where there are strict boundaries between groups, right? Nobody is moving between them. And without intergroup transmission, there's very little turnover within groups for any of those transmission mechanisms. Unbiased shows the highest rate of the four, but note that it's still quite low. And as intergroup transmission increases from the left panel to the right panel, then we see that these group turnovers increase as well in the cases of unbiased and vertical transmission, and to a much lesser extent in the case of prestige bias transmission. But the mean number of turnovers per group is unaffected by variance ceiling or by intergroup transmission under conformist transmission. Right, so another case where the effects of intergroup transmission and variance ceiling play out differently for these different cultural transmission mechanisms. And finally, we can take a look at the turnover rate results for this mixed transmission condition, right? The right panel here shows you the mean number of turnovers per group being very low when each of the four transmission mechanisms occurs with equal probability. These values are most similar to those observed under conformist transmission. So rather than seeing like an average of all four of them, which maybe what intuition could lead one to hypothesize, clearly the effects of the other three mechanisms are swamped by the occasional conformist transmission, right? And therefore the turnover rate looks much more like what we see in the pure conformist case than somehow an average or amalgamation of all four. Okay, so to summarize then, this simulation experiment illustrates that mean difference among groups and mean difference among assemblages, as well as the turnover rates within groups, are influenced by many factors, right? I've just looked at a few of them, and of course, the real world would be much more complicated than that. And if we have any hope of inferring the value of one of those unknowns of that equation, say trying to infer the mechanism of cultural transmission just from a mean difference value, then we first need values for those other unknowns, right? We first need to know what those other variables were in order to interpret, hopefully correctly, what that mean difference value would be telling us about the transmission mechanism that was responsible. And more specifically, some of these results reinforce my hunch that the task of inferring boundaries between groups in the past from the archaeological assemblages they've left behind is neither simple nor straightforward, and time averaging is largely to blame. An assemblage of artifacts is time averaged, right? A population of people is not. And time averaging causes inferential problems, no matter how badly researchers want to ignore that fact. Holding all else constant in many, but not all cases, time averaging makes assemblages look more similar to each other than the groups did at any time in the past. So time averaging alone could erase evidence of those past cultural boundaries. And for example, right, just to pick this panel here, would these mean difference values be high enough, so to speak, for us to correctly identify the presence of strict boundaries between the groups that created these assemblages? Now, maybe a value of 0.4 empirically would be considered high. A value of 0.1 probably would not. But of course, this depends on your expected value, right? And if we don't have a good, solid foundation for generating those expected values under these different conditions, it's probably less likely, right, that you would recognize a relatively low value for mean difference as being representative or indicative of these cultural boundaries when those assemblages have been time averaged. Okay, so in answer to that question, how likely would it be for us to correctly identify this? Well, it'd probably be pretty hard, at least not without a prior information regarding the mechanism of the transmission or the degree of time averaging. I've also learned that it's not simple to infer mechanisms of cultural transmission responsible for the observed level of differentiation among these time averaged assemblages. So there are multiple ways to get relatively high mean difference values between assemblages in this simulation. So a high mean difference value does not necessarily indicate strong conformist bias transmission within groups, given the starting conditions of this model. Conformist transmission is one possibility, of course, but there are others as well, including unbiased and prestige bias transmission, assuming that intergroup transmission is very low or absent, and that there are sufficiently many different selectively neutral variants of the trait, and that the copy error rate is sufficiently low relative to the degree of time averaging. So these are all empirical questions that need to be addressed before we can infer transmission from an observed mean difference value. And I also learned that the homogenizing effects of time averaging hold, even if we relax the assumption that the trait is always passed via the same mechanism of cultural transmission. So, here we're looking at that mixed condition case, and consider an empirical value of 0.2 from a heavily time averaged assemblage. Given only this value, how likely would it be to correctly infer that this resulted from a little bit of intergroup transmission, right, about 1% per generation, and a trait that was passed via each of these 4 mechanisms of transmission with equal probability? It's probably pretty unlikely that we would arrive at this inference just from that mean difference value alone. So these are all the reasons behind my response to Jelko's question regarding whether the conclusions about transmission were warranted by the values that they had observed, right? I said, well, it depends. And the confidence that I would place in the interpretation depends on the values of these other factors. The values for those other factors were not provided in that particular study because we looked into it, but that's not anomalous, right? Most studies do not provide those values. So then that leads me to my discussion and my concluding points here. And that is that we need to answer basic questions regarding the traits we study in the archaeological record before we start drawing boundaries around Paleolithic culture areas, or before we start divining the mechanisms of cultural transmission responsible for the variation we observe. Now, I realize that message is a bit of a buzzkill, right? So, can't we please just skip to the good stuff without addressing all these rather pedestrian and totally uncool methodological questions? And, okay, I get that sentiment. But at the end of the day, one skips these steps at one's own peril. And, you can't say you weren't warned. And to be honest, I think people will be surprised by how much we stand to learn by attempting to answer these relatively simple questions for the kinds of traits that archaeologists study. So what are these questions? I'll go over them in a little bit of detail here because I promised that I would, just to give you a better sense of what we can gain by addressing these. So question number 1, does the trait in question vary continuously or categorically? Now, my talk focused only on discrete traits where variants vary categorically. I have published papers in the last couple of years that deal with continuous traits. The point I want to make here is that there's a big difference between the two, but you'd be surprised by how few people take this difference into consideration. Many archaeologists I've spoken to haven't thought much about this distinction because they don't really see why it matters. But it does matter because the two types have very different types of copy error models, and that can lead to different expectations regarding how variation is partitioned within and between groups. Question number 2, are the variants of the trait selectively neutral? That is, do different variants of the trait provide differential fitness benefits, or are they all equivalent? Again, today's talk dealt only with selectively neutral traits, but that doesn't mean that I think that assumption holds true for most artifact attributes. If some variants function better than others, this can also affect variation within and between groups, independent of the way in which they're transmitted. 3, what is the likelihood that a naive individual would adopt a different variant of the trait than the one she was trying to learn from her teacher? So basically, here we're asking, what is the probability of making a copying error during transmission of this trait? Are these errors rare? Are they common? How would we ever know how likely this was during the Oldowan? although this is a difficult question to answer, as you saw, copy error does modulate the effect of some of the other factors like time averaging. So if we don't know the answer to this question, then we need to be aware that this could come back to bite us during interpretation. 4, which model of copy error is appropriate for the trait in question? So if we're dealing with discrete traits, then we've got the infinite variance or finite variance models of copying error. The latter is appropriate for almost all empirical cases, but sometimes the estimates archaeologists use are based on the former, and this could lead to a disconnect. And when we are dealing with a finite variance model, when it is more appropriate, which I think is, probably in almost all cases, then how many different variants of the trait are possible, right? How many different ways are there to skin the cat, so to speak? Are we talking 2 different ways, 10 different ways, 100? This number matters because if there aren't many possible variants, then we should not expect much of a difference between regional populations or their assemblages, regardless of the type of cultural transmission in play. In fact, in this case, where we don't have many different ways of skinning the cat, so to speak, we shouldn't expect much of a difference between regional assemblages, even if the trait was learned individually rather than passed via cultural transmission. Number 6, how often were variants of this trait transmitted between groups in the structured population, either through contact or through migration of people, right? So this is what we looked at with the intergroup transmission rate in the model. And to be honest, we probably will never know this value for the Paleolithic, but that doesn't mean we can ignore it. And instead, I think we have to recognize this as a blind spot and incorporate it into our uncertainty as best we can. And the final one there has to do with time averaging. How time averaged are the assemblages that archaeologists have to make these comparisons? Are the assemblages time averaged to different extents, such that some assemblages might conflate tens of thousands of years more than others? Because time averaging alone can affect mean difference, this is something that we need to know before attempting to interpret those values that tell us about the differences between assemblages. It's unlikely that all of the assemblages used in these, so-called big data comparative studies will be time averaged to the same extent, and that will probably complicate things. Okay, although these may seem like simple questions, it's probably clear that they don't have simple answers when it comes to the kinds of traits that Paleolithic archaeologists have to study. And my archaeologist friends get frustrated, pretty quickly when I start asking these questions, and rightfully so, right? They are difficult questions. Most of them admit that we don't have answers that inspire much confidence for some of these questions. And I, for one, think it's okay to admit that, right? The simple questions we can't answer teach us important lessons. By making plain what we don't know, or perhaps we'll never know, or maybe can never know, at least they force us to reevaluate the confidence we placed in earlier interpretations. I'm not often impressed by the kinds of studies that that Jelko brought to my office that day a few years ago, mainly because none of them address all of these questions before jumping to conclusions regarding cultural transmission in the past or the presence of these past cultural boundaries. In my opinion, we still have a lot left to learn, and to have any hope of keeping between the ditches on this long winding road, I think we need to ask the right questions in the right order. Unfortunately, I think many studies to date have skipped over most, if not all, of these questions that I've listed here. And as a result, I think their expected values, the values that they're comparing to their observations, suffer. On the positive side, though, I think we can improve our study of Paleolithic group boundaries, as well as our inferences about the mechanisms of cultural transmission in the past by addressing these questions more regularly and deeper than we have before. And the goal of the paper that I'm working on with Jelko that that presents this model and these results, the goal of that paper is really to convince more people to do just that. So we'll see if that is successful or not. Now, clearly, I've tried to be a bit provocative here at the end. I'm looking forward to your thoughts on this. Hopefully, you can set me straight. Thank you for sitting through yet another Zoom session, especially one that had technical difficulties, as they all seem to. I'm happy to address your questions as best I can. I know we got a late start, so we don't have much time left. So if you don't get a chance to ask your question today, please feel free to email me at this email address at your leisure. Thank you.
Thank you very much, Luke. We all really appreciate all the work that you put into that and the clear way you presented those complex results. Thank you so much. And as you said, we don't have much time, so I'll just open up the chat if anyone wants to ask a question now for Luke in our waning minutes here. And I would appreciate you just putting up your hand. And if you can see on the right-hand side of your screen, the participants list, if you see anyone with their hand up, feel free to call them. And Luke.
Okay, yeah, Daniel has his hand up.
So thanks, really, really interesting. It seems to me, I mean, to add being a downer on top of being a downer here, you know, a lot hinges on selectively neutral, and yet if there are cultural forces at play, then even things that don't have any functional significance have social significance. And you can't, so then you have a chicken and egg problem with regard to the existence of cultural transmission, right? If it exists, then the ethnic marker component may matter. And if the ethnic marker component may matter, then it's not selectively neutral.
Yes. I'm not opposed to adding downer on top of downer, but maybe I'm just pessimistic. But yeah, I see your point there. And there are so many subtle nuances there that probably are going to be outside of our grasp, given the resolution of the data that we have available to us. It may be, though, that I could or someone could incorporate that notion into a structured population model like this to see if, in fact, it does provide a different kind of signal, right? It doesn't seem like it would to me, but I'm often proven wrong by doing these models, right? I don't trust my intuition much anymore. So that would be, even though I agree with the sentiment there, it may be something that one might want to include in additional simulations to see if, in fact, something interesting does pop out. Sometimes it does, but I don't see how it would in this case.
Yeah, if you do pursue that, I just encourage you not to equate that ethnic marker component with conformist bias, because you can have, for example, vertical or prestige bias and still have ethnic markers, right?
Yes. Yep, thank you.
I have a question. So obviously there's many different permutations of these models that you could run through, and you showed us, and you previewed some of the other kinds of work that you would be interested in pursuing. I'm wondering about the model of intergroup migration and intergroup transmission, because that's, thought to be a really key feature of, maintaining connectivity in a large group of cultural models, provides scope for, greater fidelity in the long term and some traits. I'm wondering whether you have some permutations of the model that might adjust the migration assumptions. Like when I was looking at your migration assumptions, I thought that, putting in a kind of a gravity model about where you're likely to migrate rather than a full randomization. And then also the interesting phenomena with, at least in modern human populations, with migrations usually form streams where you have kind of a path dependency, where the one migrant between any place is going to increase the likelihood of a second migrant between those places. And you have these forward and back channels of migration. So that when I was thinking that through, I was wondering if something like that, which at least would be ethnographically realistic, not necessarily for the old one, but would perhaps serve to preserve some of the diversity in pockets rather than fully diffusing variation between groups. I don't know if you have any thoughts on that.
Yeah, so that's a very good comment and question. To answer the first part first, have I done anything else with migration before getting to your second one? The only thing I've done with migration that I did not show you is that I made it spatially explicit, so that you would be more likely to move to groups that were near you than to any of them chosen randomly. And given the mean difference values that I calculated, that doesn't make much of a difference. But if I had done more of a spatial analysis, right, where I was looking at the clustering of different variants in space, then doing it spatially might have more of an effect, right? As to your second one about interesting ways to incorporate some ethnographic observation into a different way of doing migration. This kind of path dependency one, where earlier migrations would increase the probability of future migrations, right? Like, kind of like, ants using chemical trails to make a path, and then they follow that path or then going other places. That would be really interesting. And I think something like that, a non-random way of organizing movement between groups probably would change even these mean difference values that I'm calculating at the population or assemblage scale. And it would be interesting to see how that plays out with time averaging as well, right? So part of that would be dependent upon how long those trails last, right? Or how long that those previous interactions between groups influence future ones. As long as there would be some movement between them, then maybe that time period, the decay period wouldn't be as important. But there may be situations in which those trails, do decay. And if they decay quickly enough, then maybe that wouldn't have much of an effect on these kind of, coarse grain scale measures that archaeologists are able to deal with. And that would be interesting to look into. The problem, as you mentioned, though, is that, even though that might be interesting from kind of a theoretical point of view, and even though it may be, applicable to ethnographic cases that you have in mind, it might be tough to sell that for, learning about what the Paleolithic has in store. Because I would be, in a sense, arguing that migration worked that way, or intergroup transmission worked that way. And of course, I don't know that that's the case, right? So I also don't know that it was, or think that it was completely random either. But usually we start from, that end of things, and then work our way towards more detailed or specific examples as needed. And that may be a reason to hold off on that at the moment, but it would be a cool thing to look at. Or maybe it would even be a separate model, right? That could be applicable to the ethnographic case, where data from the field might actually help parameterize that kind of method. And that would be pretty cool and interesting to look into.